Hello and welcome to I guess this is the almost November but still October edition of the Community for F Sharp, formerly known as Live Meetings, now Hangouts. Today we're pleased to have Gabriel Kako presenting on his work on the F Sharp for OpenCL FSCL project. We'll get to him in just a moment, and before we do, I want to just mention that if you're running a user group or a meetup and are looking for some resources to help you with that, check out c4fsharp.net. We have a number of dojos and some workshops and some other community content. If you're just a member of the F Sharp community, we also have a list of events and user groups that you can join. So please check that out. If you look at the showcase in the Hangouts window, you'll see a link to Community for F Sharp, as well as the FSCL project on GitHub. With that, I would like to introduce Gabriel. Gabriel is a PhD student in computer science at the University of Pisa. His research is mainly focused on metaprogramming for parallel and distributed computing. He is also a senior software engineer in BioBeats, a Californian startup working on adaptive media, where he mainly covers mobile UX, UI, and code optimization for mobile and wearable devices. Gabriel, thank you so much for joining us, and we're looking forward to your presentation.
Thank you. So I'm really glad to be here today. I would like to talk about my PhD research, which is actually turned into this kind of product of this framework, which is FSCL. I'll just give a brief overview of the purpose of the framework and how it was born, and then I'll try to focus mainly on how to use it, because I would really like you to use it, and so we'll do some kind of live coding using it. So just let me give you a brief introduction using some slides. Let me share them. There we go. Okay. So here is it. So just the very first idea behind FSCL. FSCL, if you don't know it, it stands for F Sharp to OpenCL. So the idea is to raise abstraction and simplify things on OpenCL, where things are programming but also executing things on the OpenCL platform. So the situation now is that we live in a very heterogeneous world. We have a lot of devices today in our computers, in our laptops, in our mobile platforms, and also in wearable devices. We have CPUs, GPUs, now we have APUs, which means CPUs and GPUs integrated into the same chipset die. And if you think about it, every smartphone today has two different computing resources. For example, a CPU and a GPU on an iPhone or some Android smartphones. We have those two resources, and this is also true for every desktop and laptop CPU that you buy today. An Intel Ivy Bridge has two resources as an integrated GPU, as the mainstream AMD CPUs. So the fact is that with all this heterogeneity, it's really hard to understand what's going on behind. So it's very likely that all the people that buy these resources and that can program and that can work on these resources are not aware of what's behind the curtain, so what's in their PC, in their systems. So. And this is very likely turning into an overspending or an underutilization of resources, because I don't know where my computation, where the things that I execute is going to effectively run. So the problem is that we need some kind of things that help us to simplify programming, because all these resources are becoming really cheap. So every programmer is actually programming for or on a machine that has multiple resources, but also we have to help people to exploit all these resources from time to time in a dynamic way without putting the burden of choosing the device and to understand the platform on the programmers. So the work itself is mainly based on two considerations. So the first is to provide an homogeneous programming layer, quite simple to write parallel things on OpenCL. And the second is to provide something that OpenCL doesn't provide, which is a way to understand the differences between the characteristics of the various platforms, of the various devices, CPUs, GPUs, accelerators that we may have on our system, and automatically schedule on the particular device from time to time, depending on the particular program or computation that you want to execute. So these are the two key points of my research, and those points are important because OpenCL is really widespread, is a specification for heterogeneous parallel programming. A lot of people are using it, but it's widely supported by the majority of silicon producers. But unfortunately, it has some drawbacks. It is low level, it is error prone, it is JIT compiled, which means that I discover errors in the kernels, in the things that are in the computation that I code only when I write and execute a program that compiles them. So it's kind of like two levels. So it's a waste of time to spot errors and fix them. Also, host siding is boilerplate. I don't know if you have ever programmed on OpenCL, but even for very simple kernels like summing two arrays, you have to spend a lot of time to code the host sides, which means the side that orchestrates the kernels, orchestrates the kernels, creating buffers, synchronizing with the computation, and reading back the result, and releasing and freeing the resources. So it's kind of a waste of time. So, which is, a boilerplate, which means most of this code is ported untouched from time to time, so we may automatically generate it, saving time for the programmers. So we have many difficulties, and for this reason, it's hard to program OpenCL, even though it is really so widespread. Also, it has this drawback, which is the fact that it doesn't provide any help to optimize computation across multiple resources, which is something that is quite important, because if you think about a parallel computation, it is generally very different when optimized for CPU and when optimized for GPUs, because of the two different execution models, because of the two different memory models, memory hierarchy. So, but if you want to optimize things for two different architectures, you have to do it by hand, so writing two different kernels. Also, if I do not choose any device for a computation, and I have plenty of them on my system, which one should I choose? Well, it has been demonstrated that different computations are suitable to run faster on different devices. Some kind of lightweight computation like vector addition, matrix addition, really simple filtering of images and reduction, things like that, are really faster on the CPU, because you are saving the time to transfer things to the GPU, for example, through the PCI Express bus. So it's better to run on CPU. But other computations, like just simply put the matrix multiplication, are heavily faster on a GPU. So the programmer has the burden takes the burden to understand the machine and to determine where to execute each computation. And we do want to avoid this. So this is why FSCL was born, to cope with these two issues. And it's an open source project. You can find it on GitHub. You can find it as a package on NuGet, ready to use. So just, if you want, just download it and use it. From the programming point of view, so to make parallel programming easy, FSCL introduces the ability to write all the things that you generally write in OpenCL using C99 in F# as functions. So there is a complete porting of things, syntax, data types, and so on. But you can also use higher level programming constructs. And we will see it in a moment. And from the support to exploit different devices on the same system, we implemented in FSCL a way to evaluate and analyze the code of functions that you want to run and detect from the particular features of this function where it is best to execute that computation. And we employ a machine learning approach for this. So why we choose F#? Just a brief hint of why F# is the best choice for this particular project. Well, F# is really a great language. It's strongly typed. If compared to C99 OpenCL programming, we have a higher type safety. It is really efficient. We will see that too. It is really excellent, given his hybrid nature, to create domain-specific languages, because we have a lot of constructs that we can reuse, changing the interpretation of the construct itself. So we have a lot of things that we can compose and that we can use. And also, it's open source, it's cross-platform, and it's free. So, just a brief introduction on the structure of the framework. The structure of the framework is mainly split in two parts. We have a compiler and we have a runtime. The compiler handles the compilation, the translation from F#, from the F# word, so from F# functions mainly, to OpenCL source code. So we are not targeting binaries, so we are not targeting an instruction set for specific architectures, but we are targeting OpenCL source code, which means that given it's a standard, obviously this means it's portable. So the final translation will be done later by the runtime. So the runtime takes the OpenCL source code, detects the best device where to execute, produces does the backend compilation, so producing the binary, it's acceptable, and execute a computation and return the result to the user. Everything is transparent from the user, and we will see that in a moment. So just try to see how this works. Okay, just a brief overview on OpenCL, just for the people who have never programmed in OpenCL. So in OpenCL, kernels are the things that determines what the computation has to do. So respect to the host side, that determines how the computation has to be executed. So in OpenCL, for example, a vector addition in a kernel, in parallel, you can do it. You can write it as illustrated below. So you have a sort of C function with additional constructs with some labels that associated to parameters or to the entire kernel, and generally you write C code, restricted C code to code the computation. The FSCL compiler, what it does basically is to allow to write these things in using F#, so as F# functions or static or instance methods, as illustrated in the top piece of code, and it performs the translation. But let's see this in action. So I'm gonna check if everything is still okay. So I think so. So let me switch to Visual Studio and just do a brief of interactive things. I would like to underline the fact that FSCL is fully working also on RSX and Unix with Mono and .NET Framework 4.5. I used to code really a big part of FSCL inside Xamarin Studio, for example. So everything is working on OSX2, but I really prefer the interactive of Visual Studio, so I'll use it. So just try to go through some examples. So first example is just for the compiler. If you want to use the compiler without the runtime, you want to generate OpenCL source code out of F# things, but you do not want to execute it. You may want to store it or to execute using your library, for example, instead of the runtime.
Gabriel,
So,
may I interrupt real fast? Would you
sorry.
mind zooming in on the code a bit?
Oh yeah, I tried to do it. Let me check if I can do this.
There's a little magnification at the bottom of the code screen as well, where you
Oh
can.
yeah, sorry. Yeah, I think that yeah, okay, but the interactive has the same font anyway. Yeah, okay. No problem. The important is the code. So, can you see it right now?
Yes, it looks much better. Thank you.
Okay, perfect. So, just load some libraries. You do not have to load them all if you do not use the interactive, but I'm doing it also to see all the features of the language. Generally, you just need the compiler language, which is the DLL, to write things. So there is the object mode of the language in there to code the kernel functions. And then you load the compiler just to be able to invoke this compile function to obtain the result of the compilation. Okay, once loaded, let's just write the simple example. The simplest example is like an hello world. We will do a vector addition, really simple put. So what we do is this. We open some namespaces, system reflection, which is used to have some attributes that are required to understand, to mark that a F# function is actually an OpenCL kernel. And then we open, as I said, the language and the compiler. Then let's try to define a kernel. To define a kernel, you define a function which can be a module function, an instance method, or a static method, or even a lambda if you want. But let's do it simple and try with the module function. So we define a function that takes this is a particular parameter that encapsulates all the information, as you may see, all the information about the current thread, which is the what is called the work item in OpenCL, as the global ID and the local ID inside its group and all the other things. So this is required. All the other parameters obviously depend on the computation. Now we want to sum two vectors, A and B, and to write the result into C. So these are the parameters. And inside the kernel, what we do is to take every thread, every work item takes its global ID and sums the matching elements of the two vectors, writing then into C. So we can take this and send it to the interactive. So now, once we have defined an F# function, which is actually an OpenCL kernel, to compile it, we instantiate a compiler, and then we tell, okay, let's compile something. This something is a quotation, is an F# quotation. The quotation can contain the kernel in many forms. It can be a reference like that, but it may be also a function call if you want, and we will see it later. So just say that we want to compile this, and the result is a kernel module. Now, let's try to see what this kernel module, which is the result of the computation, contains. The most important things, I think, is that it contains OpenCL code. So now let me check if fortunately I cannot zoom on this, but I can do this. So this is the result of the computation, which is, as you can see, a C code. So the F# code of this kernel is translated into OpenCL source code. Then we have many other informations, like, for example, there is an analysis on all the parameters that are passed to the function. And this analysis is particularly important if you want to know, for example, if a parameter is an array, is written or read, or both. For example, here, if you take the parameters and we take the first one, and let's see what happens, and try to see, for example, access analysis. The result of access analysis of the first is read access. So, which means that A is read, while the last one, for example, is write access, because obviously it's written. But if here, for example, at first I set something like this, and I try it again to compile this, and we check the access analysis of the first parameter here, as you see, now it's read and written. So this is really important because we are able to understand, to analyze the entire code and see what happens to each parameter. So this is really, really simple. You have to define your kernel, instantiate a compiler, and pass the quotation containing the kernel to the compiler to obtain the OpenCL source code together with a lot of other information. So, as I said, it's not mandatory that you pass a kernel reference like that to the compiler. You can also pass a call. Obviously, the call requires you to create some arguments. But let's see that this works too. So just, again, let's load everything. Let's create a compiler and some arguments. There we go. And we create 3 64 elements arrays, one of which is empty, which is the result. And then we try to compile the call. And there is an additional information now. Since we passed some arguments, now we have in the kernel module, in the result of the computation, we have also all the arguments that are passed to the kernel. So all these information are really useful if you want to do something with it in your custom library or whatever, but they are really heavily employed in the runtime too, which is obviously based on this part, on the compiler. Let's try to see some other things that you can do, for example. Kernels can obviously use some external functions called utility functions. This is possible in OpenCL, and this is obviously possible in FSCL too. So, for example, here we do a really simple vector addition, but the addition is not performed inside the kernel, but it's performed inside an utility function that is called by the kernel. And so if we do this, and let's try again to send this to the interactive, and we create a compiler, we create the arguments as before, and then we compile these. Now, one thing that we have is that in kernel, and then no, the kernel module, we can create, we can inspect the kernel module and see the code. And if we see the code, now, what happens is that we have both the kernel and the utility function, which is firstly declared and then defined. So, and another thing that we have inside our kernel module is the set of functions used by the compiler, used by the kernel, sorry, or by other functions. And so, for example, here we have, in our particular case, we have a single sum, which is exactly the function that we declared here, which is the utility function used by the kernel. Then, another thing.
Do you mind? I have a question about the use of reflected definition on that utility function. Do you have to declare all utility functions as reflected definition?
That's a really important question. Why we use this? We use this is needed because it tells that the function marked with this particular attribute, the compiler, the .NET compiler, has to preserve inside the IL the abstract syntax tree of this function, of the body of the function, which is the only way we can get it and then analyze it and then translate it into OpenCL. So without this, we are not able to access this, which means the body of the function. And this is the classic way. In some .NET guides, there is plenty of guides on that. This is the classic way to access things inside methods called inside quotation. So if let's put it this way, if I do not have this, the only way to express a kernel and to access the body is to declare the inside thing, is to define the entire thing as a function here. So do something like this. Function, let's say,
I see where you're going. My question was more about the helper function itself, the sum function, because I noticed it was
Okay,
also
so, okay, perfect.
decorated
So
that way.
the fact is that everything that has to be translated into OpenCL, so that has some code in C, has to have this reflected definition. In fact, if I do not use this, for example, I can expect this code at a certain point I find a method call, but I'm not able to understand what this method is doing. So I'm not able to generate the function which is as you can see, this function. And we need this, because otherwise, if I do not generate these, the OpenCL code here is invalid, because there is a call to some function that is not defined. So that's why everything I declare as a kernel, or every function that I used inside the kernel, every custom function, obviously, embedded, so native function like, I don't know, math dot, we don't have to see, math max, for example. This is not important, because there is a function that does the maximum, that comes to the maximum in OpenCL. So we generate the correct signature of pre-existing function. But if you want to use some custom functions that you define, you have to use the reflect definition attribute. Otherwise, you are not able to generate the code for them. Okay.
Excellent. Thank you.
Okay. So, okay, one other thing that you can do is to have multiple kernels, and then instead of compiling a single kernel call, or the reference to a single kernel, we can obviously compile a composition or a functional composition of kernel. So, for example, here we can create a kernel that does again vector addition and also returns the result. So we do kind of like this, and then we create another kernel that instead of summing two elements, it multiplies to vectors component-wise. Then again, let's pass this. And here, instead of compiling one thing, we compile many things. Many things means we have the tuple of arguments. We pass this to the first kernel, and then the result of the first kernel is passed to the second one. Here, you'll see that in the compiler, we will have one curious thing that you may wonder why is that, which means that if you inspect the code, you can see only the last kernel. So my kernel 2. This is because the compiler is the simplest possible compiler, which means that it compiles only one kernel. And in this particular case, the root kernel, which is the top level kernel, is my kernel. You can't see it really well here, but you may see it in this way if we use the classic composition, which means that we do my kernel 2 size CA, and then the last parameter is again the last argument, sorry, is a call to another kernel, which is this, and we have again nothing else, I think, or C. Yeah, ABC or C. Yeah. Anyway, let me see this. Yeah. Oh, yeah. It's my kernel. So here, you can see that we have a root kernel, which is if you want, the last kernel executed if we execute this in the traditional way, sequential way too. So the first thing is that we evaluate all the arguments. We have to evaluate these, but this is a call to another kernel. So we have to execute it, we get the value, and then we can really execute my kernel 2. So this is the top level, or the root, called the root kernel inside FSCL, is the only kernel taken into account by the compiler. Why is that? Because this, in combination with the FSCL runtime, allows to execute the entire pipeline. Because the runtime, what it does is generally this. So you have a quotation, you pass it to the compiler, and the compiler generates only the code for the top level kernel. But we have all the arguments. So if here, for example, we check km call args is, and in particular the last one, 1, 2, 3, so 0, 1, 2, 3. Okay, colargs has maybe none, so let's do this. Yeah, because we didn't do it. Okay. Okay, it's not this, it's this. Okay, if you see what is this, let me copy this here. As you can see, the last argument is another call to another kernel. So what we can do is to let the compiler to compile this. It compiles only the first kernel, but then we can walk through the arguments. And if we find some argument that is another call to another kernel, we can compile it recursively, which is exactly what it happens between the runtime and the compiler. So the runtime scans the entire quotation and generates the C code for each kernel, starting from the first one, then cycling through the arguments, and every time it finds an argument that is a call to another kernel, it compiles it first and executes it first. So after that, it can execute the outermost kernel. This is what it happens. But this is really to just to pointing out that if you try to compile things that are composition of multiple kernels, you always get compiled only the first one, and this is a choice to keep the compiler as simplest as possible. So this is mostly everything about a compiler. So I would like to go through how to execute this stuff if you want to do it, which is what you very likely do when using the framework itself. So you just switch to another script, which is this, and here we load all the compiler and runtime libraries. So let me try to show a simple example on how to run things. Again, we
get a bit again. I'm sorry.
I'm sorry. Yeah, sorry. Let me go like that. Also here, it's okay. Just close this. Okay, here again we have a vector addition. Really, really, really simple. And we create arguments as before. But instead of creating a compiler, and instead of compiling these, we run it. And how to run it? This is really the entire host code in this case, which is really, really short if compared to the general OpenCL host code. So the only thing that we have to do is to call run, which is an extension method on the quotation. And this handles all the tasks that to really execute the computation, which means allocating buffers, transferring data, finding the device, creating the context, compiling the OpenCL source code into binary code, schedule the program on the device, synchronizes with the execution on the device, reading back the result, and return to the user. All of this is handled by a simple call to run. So if we do this, and then obviously here the result is empty, so we have to check what C is. And as you can see, C is now 2 plus 3. So the computation has been executed in F# interactive, but behind the curtain is executed on OpenCL. So obviously we can, and this is really simple, so the programmer can really focus on the kernel side, so on defining what the computation has to do, and write very few lines of code to execute it actually, without spending hours to code the host side. Okay, obviously, if you love curried form instead of tuple form, you can use it. So we can do the same vector addition, but with curried form for the parameters, and this is run as well. So we have, again, 2 plus 3, which is 5, the components of the resulting array. A very important thing, which is something that instead, so far, all of this is really a simplification, is really a way to program OpenCL in an easy way, type-safe way, from within F# instead of programming C. But it's something that you can do in OpenCL as well, except for obviously the syntax changes. Here we introduce something that instead in OpenCL you cannot do. For example, returning types. Here, instead of passing, say, the first one, in first vector addition, we pass the two input vectors as well as the output vectors, and we write it. Instead, here, we do not pass any third vector. The result is allocated inside the function. We do the same thing as before, so we take the global ID of the current thread, we sum the component, we sum component-wise the two vectors. And another thing is that now, before we was like that, so now instead we return the array allocated locally, and this allows to kernels to return values, which is something that you cannot do in OpenCL. OpenCL kernels must return void all the time. So, but we can do this here, and this is really important because since now functions, kernels can return values, we can compose them in a functional way. Because obviously, if kernels do return void, we cannot compose them because the result cannot be the parameter of another successive kernel. So let's try to check this out. Now, as you can see, we do not have to create an argument for the third parameter for the result because that is created inside the kernel. So let's load this, and again, let's run this. And as you can see now, the result is no more void, is a float 32 array, which is actually exactly C, and is the sum of the two input vectors. Okay, so that's pretty cool, but obviously in F# programming, generally, if you want to do vector addition as well as many other things, you do not write a custom function for that because there are pre-existing functions, and FSCL tries to use also those pre-existing functions which come in handy when you want to do kind of simple things like this. And in particular, in F# we are talking about array map, or about more generally about on array reduction, map2, reverse, and things like this. We have plenty of collection functions that we can use on both arrays and lists. So, for example, if you want to, in the specific case, if we want to do arrays, we do not define a function called vector add. We simply use array map2, clearly, where the function applied to two elements of the two arrays is the sum. So, for example, here we can simply create two arrays, define a function that does the sum, and then instead of creating a custom kernel, what we do is to invoke array map2. And if we do this, sorry, here. There was an integer somewhere. This is full 32. Okay, let me check this out. Probably. Oh no, sorry, I had to reload it. There was something in the interactive environment. So as you can see, let me do this again. We can run in parallel a vector addition without creating custom kernels, but simply using pre-existing F# function. I think that all of you have seen this function and used it a lot inside the functional part of F# programming. So you can still use it, but instead of executing it in this way, you wrap it into a quotation and you call run on it. It's the only sequential execution to parallel execution on OpenCL. Well, one other thing that we can do is to avoid, another thing, furthermore, is to avoid this. In fact, what you can do is instead, let me just change this instead of to moving to the next sample. Instead of defining a function to do the sum, what an F# programmer generally does is to remove these and say fun a b in a plus b. Just do not avoid some confusion. It's obviously working, but let me just change the variable names to make it more clear. So we have a map. We use a lambda to define what to do on each pair of components of the two arrays, and we run it. And this, again, it's working, and it's run in an OpenCL. So to do some kind of things that can be expressed using map, map2, reverse, reduce, scan, or fold, it's called fold in F#, all of these, or composition of these, can be executed in OpenCL without any change in the syntax, but simply wrapping into a quotation and calling the run method. Okay, that was this example. Here we have another pretty example about a more complex kernel. We are doing a matrix by vector multiplication, and there is another thing that in OpenCL you cannot use it, but in F# you can, which are multi-dimensional arrays, array 2D. In OpenCL you are forced to use flat arrays, 1D arrays. Here you can use 2D arrays, and the runtime and the compiler handles all the burden of flattening these arrays. So you can clearly do this, which is a bit more complicated, a vector addition, and run it and obtain the result, which is we have a 64 by 64 matrix. Every element is 10, so the result is clearly 64 by 10 multiplied by the 1280, which is exactly the result. So another thing that is kind of important when you code in FSCL is that it's really easy to debug. So in OpenCL, the problem is that things are running on devices more likely, and often they are GPUs, so you are not really able to debug on them. There are some custom or some third-party tools, or also integrated tools in the AMD, for example, SDK, that with which you can debug on GPU, but sometimes it's a bit tricky. Here, what you can do is really simpler. So let's try to again see matrix by vector. It's really simple, but here we have a mistake. So let's see, and we are not able to spot this mistake. So let's try to load it. It loads correctly. Then we create the arguments, and then we run this. If we run this, oh wow, the result is 0. It's not 1280. Why is that? Because we have a problem. But one thing that we can do is to debug really easily, is to change this run, and instead of running in the traditional way, which means on OpenCL, we run on multi-thread. If we run a multi-thread, this is invoked by reflection. We are not generating any OpenCL code, anything like that. We are simply invoking by reflection this function, obviously executed on the CPU. So we are able to put breakpoints and to stop and to see what happens. This is clearly if you are not in the interactive. So the idea is that when you find something that is not working in your kernel, even though the kernel is executing correctly, one thing that you can do before putting some logging prints or something like that is just to change from run, which is OpenCL, to run multi-thread. So you are able to put very handy breakpoints and to stop into the function. Also, you can use run multi-thread every time you want. You do not want to run something on OpenCL because you think it's, for example, two-way lightweight to execute on OpenCL. It's better to use multi-thread. FSCL supports multi-thread for kernel execution. Simply a change of the function you called on the quotation. Then, just another thing is that you can compose kernel. I already told this when we saw the compiler thing, and as I said, the compiler is only compiling one kernel at a time. But when you run it, the combination runtime and kernels, and runtime and compiler together are able to compile and execute also combination of kernels. So in this particular case, we have again the matrix by vector multiplication. Okay, I missed one. Just this. Right. And then we have another kernel, which is the vector addition. So the idea is that before, at first, we want to multiply a matrix by a vector, and the result, which is a vector, obviously, is summed to another vector. So we can do the first and then the second. So what we can do, again, is to create a matrix, a vector, another vector, and then we can, instead of executing one kernel at a time, we can put the combination inside the quotation. So here, we execute a matrix by vector multiplication, and after that, we sum these, the resulting vector, to another vector, which is something that you do also in traditional FSCL programming. So you can compose function is the most natural thing for a functional programmer. And as you can see here, the result here was 64 by 10 by 2, so it was 1,280 multiplied by 2, because we are summing 1,280, and the result is correct, to 2,560. So with this simple composition of function put inside a quotation, then we call run. All of this is executed on OpenCL with successive kernels, and the runtime is able to handle all the issues down here, which are executing the kernel, synchronizing, reading back the result, make sure that the result is available to the second kernel, execute the second kernel, and returning the result to the user. So all of this is transparent to the user. Obviously, since you are FSCL programmers, you are really, it's really likely that you like more this kind of composing function, so instead of this, which means with pipelining, and you obviously can use it, it still works. And it's also some kind of more intuitive, so we take some data, we execute the first kernel, and then we execute the second using the result of the first one. More and more, you can also compose custom kernels with collection functions. So, for example, array map or array reduction. So, for example, here we want to, again, do matrix by vector multiplication. And then what we want to do, for example, is to sum all the elements of the resulting vector resulting from matrix multiplication. So what we can do is to do matrix by vector and then pass it to a reduction. It's really, really simple. Just let me cut off the last one, which is something that I tell you later. So what we can do is matrix by vector and then array reduction. And we can do it because because the compiler and the runtime are recognizing this is a custom kernel, so we generate a custom OpenCL C function for this, and this is a very specific function that the compiler recognizes and generate the reduction parallel version in C and execute it in OpenCL, and the result is here. One last thing that I would like to tell you is that sometime inside your pipeline you may want to execute something in sequentially on the CPU instead of executing it in multi-thread or OpenCL. So, for example, here we may want to do matrix by vector, then collecting the sum, computing the sum of all the elements of a vector, which is obviously a scalar value. Then we want to check if the scalar value resulting from the reduction is greater than 100, then let's say 100. This is a threshold. Otherwise, it's A. And after that, we want to, for example, multiply the components of a component wisely, the elements of a vector by this constant, so the result of this. So what we have here, we have a pipeline of 4 things. The first is, I marked this function with reflected definition, so it will be an OpenCL kernel in parallel. This is an OpenCL kernel in parallel because it's a collection function, and it's recognized like an OpenCL kernel. Then we have this. This is a function that is not parallel, obviously, and it's simply a check, a condition check. So this is able, the FSCL runtime and compiler are able to detect that this is not a parallel function, obviously, and so they do not generate an OpenCL kernel for this. But simply put, after having executed the first 2, the result is taken from the device and transferred to the host. We execute this, and then we pass it to the last phase. And the last phase is vector mode, where vector mode is again a reflected definition. So it will be executed on OpenCL. And the cool thing here is that you can compose custom kernel, collection function that has to be executed in the traditional way on the CPU, and again, OpenCL kernels, all inside a single quotation. So just try to do this. And if we do this, it is executed correctly. So the idea is that you can mix multiple things in the same way you generally do in traditional F# programming, but the thing is that the syntax is not changing, but thanks to reflection and many other features of virtual execution environment, we are able to execute on OpenCL in parallel all the things that are proper to execute in parallel. So, okay, these are mostly all the things that I would like to tell you in a very short introduction on OpenCL, on FSCL programming. There is plenty of other features that I would like you to test, and you can see the documentation for that and on GitHub, and also there is one contained in the NuGet package. But before leaving, I would like also to tell you about one other thing which is really important about FSCL, which is device selection. As I said, it is really important to help people to select a device. So one thing that we can do to select a device in OpenCL, in FSCL programming, is to use custom metadata, so custom attributes. So for example, what happens when I execute this kernel, for example? So by default, the kernel is, if you have many OpenCL enabled devices, for example, a CPU and a GPU, the default behavior is to execute on the first device. But we may want to force this, and we can do it by saying, okay, let's use a different device. For example, the second on the first platform. So the platform is the first. Generally in OpenCL you have a platform number, and also when you list the platform you have a platform number, and inside the platform you can list the devices. So here we have the platform number, second device, or platform, or first platform, first device. So we can mark the kernels to force the execution on particular device. But if we do not, the idea is that it would be, the best thing would be to analyze this code and check if it is more suitable for CPU or more suitable for GPU. And this is exactly what we are working on right now on FSCL, and we are trying to deliver it soon. So I'll give you a brief introduction on that, really, really brief, which is here, just the scheduling end. So the idea is that we want to leverage on multiple different CPUs, GPUs, or devices in general that we have available on our platform. So what we can do is to use our approach is based on machine learning. So what we do is that we extract some features from computation, where features may be, for example, the number of memory accesses, the number of branches, and sort of number that encodes the branch prediction, for example, the number of conflicts in accessing memory, and other things. All these things can be extracted from the computation, and then when we have those features, we compute using a classifier, we compute how each feature is contributing to a particular completion time on a device, so that when we want to execute a successive kernel, what we have to do is to extract the same features and then using what are called the regression coefficient to predict the completion time on all the devices, and then we pick the fastest one. So this is exactly what we do, and this is really handy to do this in F#. This is because since we have the quotation, we have access to the abstract syntax tree, and so we are able to extract all those features. For example, to extract the number of memory accesses, we can simply walk through the AST and check which nodes are encoding a memory read or a memory write, and then sum these +1 to a particular counter. So we can do it really easily and transparently because we are using F# and we are using quotation. Also, another thing that we can do is in F# is not only walking through an AST, but we can build AST, so we can create expression, which is what we do in our scheduling engine to fasten and to speed up and make it really efficient to calculate features at runtime. So the first time we see a kernel, we walk through it, but some features like the memory accesses may depend on the arguments, and the arguments are not known. So what we do is to create a sort of parametric AST, which will be finally evaluated only and every time the arguments are known. So every time I call a particular kernel providing a different set of arguments. And in this way, most of the computation to extract features can be done only once the first time a kernel is seen, and a very small amount of computation is left every time we execute a computation with different arguments. And we are going to release a paper on that, but I can tell you that generally on the CPU I'm using for testing, which is an i3 something, I think is 5420, like that. It takes, at runtimes, it only takes less than half a millisecond to compute the feature values and to establish which is the best device where to execute the computation that we want to run. So really fast at runtime. Okay, so we have some early results on the efficiency and the reliability of scheduling on particular devices. For example, here we see that matrix multiplication, then we have another version of matrix multiplication, then we have convolution is another algorithm, can be scheduled on the right device, really often. For example, in a matrix multiplication, the naive version and the optimized version, we have about the 100% probability to right guessing the best device, and so to make it as fast as possible. For other algorithms, the reliability is a bit lower, so the right guesses probability is a bit lower. But anyway, we are trying to improve it by extracting more and more meaningful features in the future. So the last thing that I would like to tell you is that sometimes people are a bit scared about FSCL because they say, okay, I'm not a physicist, I do particle things, I'm doing fluid dynamics, I really need high performance, and I ensure that C or C++ is delivering highest performances, so I'm staying with OpenCL. So this is not true at all. In fact, FSCL is really highly optimized. Obviously, I coded it myself, so it may be optimized if I had more time or more people working on it. But anyway, it's still really efficient. In fact, here you can see that vector addition, the difference in completion time between the OpenCL C version and the FSCL C version is really small. It's at the beginning, it's kind of like 0.1 milliseconds, so really small, and at a certain point they converge to each other, so they have the same execution time if you execute it on .NET F# or in C. And the same for matrix multiplication. As you can see, matrix multiplication, sometimes the F-sharp version outperforms FSCL. This is mainly due because of memory pinning, but anyway, generally the performance are the same. So if you are worried to use FSCL because you think C is faster, is not all the time it's like that. So you may use FSCL successively without losing performances. So just, I would like just to tell you that if you want to extend the compiler or the runtime, they are plugin based, really simple to extend. I will write a tutorial really soon about that, but they are fully extensible. The compiler can be completely replaced with other steps, and you can put into the compiler the support for additional data types if you want. So they are originally thought to be completely extensible. We have a lot of features perspective on FSCL, for example, handling parallel execution on cloud computing, on Azure, for example, or scheduling on the devices instead of with a completion time approach, with an energy consumption based approach. So you schedule on the device that consumes less energy, which may be really the key, may play a key role in saving, for example, memory mobile batteries. And I would really like to conclude this with telling you that if you want to contribute to this project, it's really, I would be really chuffed to bits if you would like to. And these are all the references about the GitHub repos for the compiler and the runtime. You can find FSCL on my website with a bunch of tutorials and guides and also ideas and thoughts about FSCL. There is an FSCL Twitter account if you want to follow me, and also my personal mail and Skype contact if you want to call me to talk about FSCL or whatever else. So thank you very much.
Thank you very much, Gabriel, and thank you all who attended. This recording should be posted on our YouTube feed very soon, our YouTube channel, and I will be sending out a link through our Twitter feed at C4F Sharp when that is ready. Gabriel, thanks once again very much for your presentation.
Thank you very much. I hope you enjoyed it, and let's keep in touch. Thank you.
Absolutely. Have a wonderful day, everyone.
Thank you.